On May 8, 2025, high above Chelyabinsk, Russia, an asteroid heavier than the Eiffel Tower entered Earth's atmosphere and exploded about 19 miles above the ground. The blast outshone the sun, but because of how high it was, it took over 90 seconds before anyone heard the shockwave. That eerie delay only made things more unsettling. Security footage and cell phone videos captured people gazing at the sky, watching a glowing smoke trail stretch across the clouds. Then, boom! The shockwave struck. Windows shattered across the city. More than 1,000 people were injured, most from flying glass as they watched from behind windows. In total, over 7,000 buildings were damaged and about 1,500 people hurt. And to add a twist of irony, scientists had predicted a different asteroid, named Duende, would pass close to Earth that same day. They were right. Duende flew just 17,000 miles above Earth, closer than many satellites. But the Chelyabinsk asteroid? Nobody saw it coming. It was unrelated and completely undetected until it exploded in the sky. That's not as rare as you might hope. Even with modern telescopes and technology, spotting incoming asteroids before impact is still something we're surprisingly bad at. Since 1988, more than 1,200 asteroids over 3 feet across have hit Earth. We only spotted 5 of them ahead of time, and never more than a day in advance. So, why are asteroids so hard to detect? And if a big one were coming our way, could we actually stop it? Milky Way: where do asteroids come from, and why are they hard to see? Asteroids are ancient space leftovers, remnants from when the solar system formed about 4.5 billion years ago. Early on, rock and dust collided and clumped into molten baby planets. Heavy metals like iron sank into their cores, while lighter materials stayed up top. Some of these bodies grew into full-sized planets. Others crashed and shattered, leaving behind fragments, asteroids. Some of these are solid metal, like the iron meteorites we occasionally find on Earth. Others are basically space gravel piles held together by gravity. Most asteroids hang out safely in the asteroid belt between Mars and Jupiter. But some get nudged into orbits that bring them closer to Earth. These are called near-Earth objects, NEOs, and they're the ones we need to worry about. The late Stephen Hawking once called asteroid impacts the biggest threat to life on Earth. But spotting them is tricky business. From the ground, astronomers look for faint moving dots against a backdrop of still stars. But asteroids are small, dark, and don't reflect much sunlight. On average, only about 15% of what hits them. They're easiest to see when they're fully lit, which usually means looking in the part of the sky opposite the sun, a phenomenon called opposition. More than 85% of known NEOs were found during that brief window of visibility. But if an asteroid is coming from the direction of the sun, like the Chelyabinsk one, it's almost impossible to spot. We've identified about 1 million asteroids so far. Around 24,000 of them are NEOs, space rocks we track closely. Telescope tracking the threat. What we know, and don't. Even once we spot an asteroid, figuring out whether it's going to hit Earth isn't easy. Observing it for just a few days isn't enough to predict its path with certainty. We often need years, sometimes decades, of data. And even then, predicting asteroid orbits is messy. Their paths get tugged by the gravity of planets, the moon, even other asteroids. Over time, those small shifts add up. Thanks to something called dynamical chaos, there's a limit to how far into the future we can reliably predict an asteroid's path, usually about 100 years. And that matters because we know big impacts have happened before, and will happen again. Whole case in point. Meteor Crater, Arizona. If you've ever driven through northern Arizona, you might have seen the Beringer Crater, a massive mile-wide hole in the desert. It was created about 50,000 years ago by a 164-foot-wide, 50-meter, iron asteroid. When it struck, it released the energy of about 10 megatons of TNT, over 600 times more powerful than the bomb dropped on Hiroshima. The man who studied the crater, Daniel Beringer, thought he'd find a giant chunk of iron buried underneath. He drilled for 27 years, but found nothing. The asteroid had vaporized on impact. That's an important reminder. Even smallish asteroids, just 50 meters across, can unleash devastating force. Chelyabinsk was only about 65 feet wide, yet it injured thousands. Sauropod the dinosaur killer, and could it happen again? The most infamous impact in history happened 65 million years ago. A 6-mile-wide asteroid slammed into what's now Mexico's Yucatan Peninsula, triggering a mass extinction that wiped out the dinosaurs. It launched molten debris across the globe, heated Earth's atmosphere, and cooked everything not underground or underwater. Could something like that happen again? Yes, but probably not in our lifetimes. Asteroids that size only strike once every 100 million years. Statistically, the odds of one hitting during your lifetime are around 1 in a million. Better still, we've already mapped all known asteroids in that size range with Earth-crossing orbits, and none pose a threat for at least the next 100 years. Grimace, but what about the smaller ones? Here's where things get worrying again. For every massive asteroid, there are thousands more in the 300–2,500 foot range. That's still big enough to obliterate a city or region. We think we've discovered about 98% of the largest ones, but mid-sized ones? Not so much. Many of those are still unaccounted for, and they're small enough to slip by undetected. Rocket, what if we did spot one? Could we stop it? The short answer, not yet. Blowing one up might just scatter the danger into multiple chunks. Nudging it off course with a rocket would require advanced space infrastructure and years of lead time. Ideas like using lasers or wrapping the asteroid in foil to alter its orbit are clever, but not feasible with our current capabilities. Even large-scale evacuations might fail. Hurricane evacuations already show how quickly roads jam up. A real asteroid emergency could trap millions. Checkmark. So what can we do? Our best bet? Spot them earlier. We need more sky surveys, better telescopes, and more space-based observatories. If we can find dangerous asteroids decades before impact, we'll actually have time to act. With enough warning, we could build and launch the right tech to deflect them. But without early detection, we're basically helpless. Satellite. Final thoughts. Asteroids are a very real natural hazard, and one we need to take seriously. We've made progress identifying the biggest threats, but thousands of dangerous smaller ones are still out there. If we want to prevent disaster, we don't need Hollywood-style asteroid blasting action scenes. We need investment in space science, early detection, and long-term planning. Because right now, our best hope isn't stopping an asteroid. It's seeing it coming, with enough time to prepare.